Hello everyone, here we'll be discussing solving differential equations with Laplace transforms, and this actually shows how useful the Laplace transform can be to us, because notice in the last video we spent a lot of time getting used to this new idea of the Laplace transform. We even spoke about the inverse Laplace transform. I gave you some properties, and now we see the biggest property and why we care about the Laplace transform, and this is property of, well, the derivative of a function of t. So here y is a function of t, and we're going to find Laplace of y prime. Laplace of y prime is actually this. So there's a way to kind of essentially solve for Laplace of y given Laplace of y prime. So notice here we have Laplace of y prime, but here there's no y prime. So for some reason, the Laplace gets rid of derivatives, kind of, which will be very helpful when it comes to differential equations. And as we'll soon see, it actually turns a differential equation into an algebraic equation. So this is super useful. Now I'll actually prove this property to us using this proof that actually involves integration by parts, so it's not going to be too hard to follow if you know integration by parts. Then we'll extend that property into finding Laplace of y double prime, and that'll just be using this property we've already established. So let's take a look. The first thing is we want to find Laplace of y prime. So y is a function of t, so by definition this is the integral from 0 to infinity of y prime times e to the negative st. That's the definition of Laplace of something after all. Just multiply it to e to the negative st dt in this integral from 0 to infinity. And now what we'll be using is integration by parts. So we need a u and a dv to get this started. Now of course dv I'm going to let be y prime. If u was y prime, then du would be y double prime, and there's no y double prime involved here. So I want to get rid of this prime and y prime. So technically it'll be y prime dt, and we'll see what du is. Well, u has to be everything else, which is e to the negative st, there we go. Derivative of e to the negative st is itself multiplied by the derivative of negative st, which is just negative s with respect to t, in other words dt. Antiderivative of dv is just v, antiderivative of y prime with respect to t is just y, okay? And now using the integration by parts formula, we have this integral is u times v minus the integral of v du. So if you don't know, what I'm using here basically is the integration by parts formula, which says that the integral of v du, well actually it's u dv, there we go, equals uv minus the integral of v du. Perfect. So that's why I'm picking u and dv first, and then we can multiply u to v, and then minus the integral of v times du. Now this rule of integration by parts is actually proven by considering the opposite of the product rule, basically. Anyway, so now that this has been established, let's try to follow this formula out. So this integral now becomes, well, uv, so it's going to be y times e to the negative st, but since this was a definite integral, we have to evaluate this thing between 0 and infinity. And then minus the integral from 0 to infinity of v times du, which is y times negative s. So the negative s is a constant in terms of t, so I'll pull that out. And notice that negative then becomes a positive because of the double negative. And then we have y times e to the negative st. Awesome. Now what you'll notice here is that this whole thing is actually just Laplace of y from the definition of Laplace. This, if you plug in infinity, remember that e to the negative infinity goes to 0, so this thing will go to 0. Again, that's assuming that s is positive. And then when you plug in 0, so it's going to be, this basically is going to end up being, when you plug in infinity, you get 0 minus when you plug in 0, you get, well, y times e to the 0, so it's just y, but it's y evaluated at t equals 0. So it's y of 0. And then plus this, and this is exactly what we have up there. I'm missing this s in front. There we go. So this is exactly what we have right here, and so we've shown what we wanted to show, that this whole thing ends up being s times the Laplace of y minus y of 0. Nice. So that completes the proof. So now I'm going to use this property to prove this extended property. What's Laplace of y double prime? Well, if you treat y double prime as y prime prime, you can apply this property with y prime instead of y. So in other words, this is actually equal to s times the Laplace of y prime minus y prime of 0. Basically here we lost a prime here, and here we lose a prime there. So that's the same kind of idea. And in fact, with this idea, you can actually use this to extend this property to Laplace of y however many primes you want. So Laplace of y triple prime is one we could discuss, but I won't be discussing that. But you can prove it in a similar way. And since we know Laplace of y prime is this whole thing, then that means this becomes s times the Laplace of y prime, which is that entire expression above, s times the Laplace of y minus y of 0, like that, minus y prime of 0. So in total, after distributing this s into these, we get that this whole thing is just s squared Laplace of y minus s times y of 0 minus y prime of 0. So this is Laplace of y double prime. Awesome. So we have these two properties here that we'll be using extensively throughout this video. Now we're going to see an example right now where we'll actually use both of these. So let's take a look at that example right now. All right, so in this example, this is of course a non-homogeneous second order differential equation, which we could solve by method of undetermined coefficients if you'd like. Now notice y is a function of t. Now here I'm not going to solve by the method of undetermined coefficients. Actually, I'll be using the Laplace transform. First thing I want to do is establish some kind of shorthand notation, which will help us write less basically. So we're going to let capital Y equal Laplace of y. And this will just again kind of make us write less, as it turns out. So the first thing to notice is we're going to take Laplace of each side of this equation. So Laplace of that side equals Laplace of that side. So far, so good. Now the second thing to notice is that we actually know, well, kind of know what this is. We can split this up as Laplace of y double prime plus Laplace of y using that linearity property of Laplace. Here, Laplace of cosine of 2t, we know what that is exactly. That is s over s squared plus 2 squared. There we go. Now, Laplace of y double prime, if you don't remember from the previous screen, was s squared times Laplace of y, which we call capital Y now, minus s of, well, y of 0, s times y of 0, minus y prime of 0. And then plus Laplace of y from this, which we're going to call capital Y. And that's again just equal to s over s squared minus, s squared plus 4, excuse me. Good. So now what we want to do is we want to solve for capital Y. Once we solve for capital Y, that's really solving for Laplace of y, and then we can take a Laplace inverse of each side to get y by itself. That's the goal. So, right. So now what I'm going to do first is I'm going to recognize that, well, y of 0 and y prime of 0 are given in these initial conditions, y of 0 being equal to 0 itself, and y prime of 0 being equal to 1, actually. So this is 1, and this whole thing is 0, actually. So this becomes s squared. Actually, you can combine these. Look. So s squared y plus y is really just s squared plus 1, all times y. And then here we just have minus 1. Now what's really nice about this is that there's this pattern you may notice, and that's we have s squared plus 1 times y. S squared plus 1 all times capital Y. Now the s squared plus 1 could actually be kind of predicted because it is legitimately the characteristic equation of this side. So if you set this equal to 0 for yc, I guess you'd say, then the characteristic equation of that homogeneous equation would be r squared plus 1 equals 0, or in this case, s squared plus 1. Fantastic. So now what? So now we're going to add 1 to the other side and then divide through by s squared plus 1. So we have s squared plus 1 all times capital Y, just like that, equals s over s squared plus 4, and then we're adding 1 to the other side. Now to divide everything by s squared plus 1, we're going to do this. We're going to say this is capital Y is equal to this divided by that. So we're multiplying s squared plus 1 to the denominator, basically. Just like that. And then plus 1 divided by what we're dividing by, which is s squared plus 1. Perfect. at this point, we're going to use the fact that y, capital Y, really represents Laplace of y. So now we're going to take the Laplace inverse of each side to get y by itself. So now we're going to say lowercase y is equal to Laplace inverse of this side, because taking Laplace inverse of this cancels Laplace and just leaves us with y by itself. So we're going to take Laplace inverse of this whole side. So Laplace inverse of s over s squared plus 4 times s squared plus 1. Let me try to squeeze it in there. Plus 1 over s squared plus 1. Let me see if that makes it on the screen. It kind of does. Let me scoot the screen over a little bit so you can see that. So the next thing I want to do is split this up, of course. So this is Laplace inverse of the first one. Like that, plus Laplace inverse of the second one. Okay, now of course Laplace inverse of this, we kind of know what that is. Remember that when you have a constant over s squared plus a number, that should remind you of sign. And if these match in the sense that this is a and that's a squared, which indeed this is the case actually, because you have 1 and 1 squared, this is just sine of 1 times t. So this is actually sine of t. Let me scoot that over a little bit just so we have a little bit of space. Now this is going to be a little harder to do because we actually need to split this up using partial fraction decomposition. So instead of just actually cutting to the chase, I'm going to actually spend a little bit of time in this space here finding the partial fraction decomposition of this. Since these are different, we're going to write this as something over s squared plus 4 plus something over s squared plus 1. The only issue I have with this, though, is that, well, I'm trying to think if there's a kind of quick way of doing this. I don't see any fantastically quick way of doing this, but yeah, the setup here is a little unfortunate. We have to write a linear expression for the top of each of these. So we have as plus b, and then cs plus d. So this is going to be a little while to solve, but remember that we at least have Heavysets method on our side, but I don't think that's quite going to cut it because we don't have any solutions to each of these denominators being 0. So unfortunately, we'll get an equation of a system of 4 equations with 4 unknowns. Let me see if there's a different way of doing that. I don't see one right away. I kind of do see that if you were to multiply this top and bottom by s squared plus 1 and this top and bottom by s squared plus 4, if these a and c's were the same, and after foiling, you get s cubed and those cancel out. But there still isn't a fantastic way of doing that. So I'm going to stop spending time just trying to weasel my way out of it. Let's just kind of get to it. So if we actually find the Heaviside equation, again, that's by combining this to one fraction and setting the numerator equal to the original numerator. We'll get a times, well, as plus b, there we go, times s squared plus 1 plus cs plus d times s squared plus 4, all equal to the original numerator, which is just s. So now we're going to have to let s be something. So if s is 0, that leaves us with b times 1 plus c times 4, so that's 4c. I'm sorry, 4d, there we go. Because c times 0 would be 0, equals 0. So we get kind of an equation we can solve there. I mean, we can't solve for one of them, but at least there's 2, which is nice. But now what? What about when s is 1? Well, when s is 1, we get, let's see, it's going to be a plus b, that's going to be 2. So it's 2a plus 2b. That's also going to be pretty similar, but it's going to be 5 here. So it's going to be 5c plus 5d equals 1. Okay. When s is negative 1, you can kind of see what this is turning into. It's not the greatest. But when s is negative 1, we get negative a plus b, so it's b, let's write it as b minus a. But here this is going to be negative 1 squared plus 1, that's going to be 2. So in fact, this is going to be 2b minus 2a. In fact, let me just write it like this. Negative 2a plus 2b, just because we can kind of see it cancel a little bit, which is kind of nice. And here we get a similar thing, but again, negative 1 squared is positive 1, plus 4 is 5. Distribute that into this, that's going to be negative c. So we get negative 5c plus 5d equals negative 1, because s is negative 1. Now so far we need one more equation, I think, and we'll be good to go, because we need 4 equations with 4 unknowns. Now what's nice here, if you add these, you'll see that a's and c's cancel right away, and you'll get another equation involving b. And it's actually, let me see what kind of an equation. Well, so we get 4b plus 10d equals 0. So we get something kind of similar. I think what we're going to end up getting is that b and d are each equal to 0. Yeah, I don't see any way around that. That's actually clearly going to be the case here. But anyways, let's pick another value for s. The next nicest value we can come up with is 2. So plugging in 2 into this equation gives us 2a, but 2 squared is 4 plus 1 is 5. So 5 distributed into 2a plus b is 10a plus 2b. Let me say that again. It's 10a plus 5b, there we go. My mistake. Plus, again, this is going to be 2c plus d. This is going to be 2 squared, which is 4 plus 4 is 8. Distributing 8 into that, we'll get 16c plus 8d equals 2. All right, so now we have no choice but to finally erase the board. I'm going to move this over here, and then we're going to finish solving. And then hopefully from there, we can split this up in a nice way and finish the problem finally. Right, so here's where we last left off. We found y is equal to Laplace inverse of something that we broke up partial fraction decomposition-wise, and then plus something else, which ended up being sine of t. So it was Laplace of 1 over s squared plus 1 to be precise, but yeah, that's fine. Now, with this partial fraction setup, we end up with this system of 4 equations with 4 unknowns. And like I said, it's a little crazy, but look at this. If we take a look at these two middle equations and we add them straight up, we get an equation, well, two equations. Well, no, we get one equation with 2 variables, b and d still. So adding them, these cancel, so the a's cancel, the c's cancel, and we get 4b plus, that's going to be 10d, equals 1 plus negative 1 is 0. Now, of course, you can divide through by 2 if you'd like here, but it doesn't really matter, because this other equation paired with this, I believe, implies that they're each 0. B and D are actually both 0, I think. And to show this, what we can do actually is we can multiply the top by negative 4. And then when you add straight down, these will cancel, and here we'll get negative 4 times 4 is negative 16, plus 10 is negative 6. D equals 0, and that implies that D is 0 by dividing. And then, of course, with this one, if you just look at it, if D is 0, then you have B plus 0 equals 0, which implies that B is 0 as well. So this actually also implies that B is 0. So perfect. We have D and B equals 0, so in fact we can just kind of forget about these right away. And in fact, in all of these equations, we can forget about B and D right away as well, because they're each 0. So that simplifies things quite a bit. That doesn't really help this equation though, or these two equations, when paired together anyways, because if you multiply the top by negative 1, it's the exact same equation. So we kind of have no choice but to pair up one of these with this one. And I'd rather pair the top one up with that one, I think. It doesn't really matter, but yeah. In fact, you know what? Let's do this. Let's multiply this one by negative 5 to cancel out the a. Multiply by negative 5, what we end up getting is negative 10a minus 25c equals negative 5. Here below it stays the same, 10a plus 16c is equal to 2. Adding these gives us, these cancel out. Negative 25 plus 16 is negative 9c equals, that's going to be, what's that, negative 3. So then dividing by negative 9 gives us c is equal to 1/3. And now applying this into either of these equations, let's do actually into the first equation here. So this guy, applied with that, gives us 2a plus 5 times c, which we now know is 1/3, is equal to 1. Great. So this, of course, is 5/3, so that means 2a is equal to 1 minus 5/3, which, by the way, since 1 is 3 over 3, this is 3 minus 5 over 3, which is negative 2 over 3. So I'm just going to write it like this, negative 2 over 3. And then divided by 2 gives us a is actually equal to negative 1/3 now. Fantastic. So that's actually really good. So now we know exactly what this is. So specifically, this is going to be Laplace inverse of 1/3 s. And you know, actually, we can even split this up further and pull the 1/3 out of the Laplace inverse. So just to make space, I'm going to erase this real quick and do that actually right now. All right, so we discovered that a is negative 1/3 and c is positive 1/3. So if we split Laplace inverse into each of these and pull the 1/3 out, we have negative 1/3 outside of this one, Laplace inverse of s over s squared plus 4. And then here we have plus 1/3 Laplace inverse of, well, I guess it's also s over s squared plus 1 now. Plus sine of t. I think that looks okay because remember a and c were equal to 1/3 and negative 1/3. Well, a was negative 1/3. And now we know exactly what this is, similar to how we found that being sine, but since the numerator is s, we get cosine of the square root of these numbers. So this is negative 1/3 cosine of, since that's 2 squared, it's of 2t, plus 1/3 times, that's going to be also cosine of 1t, and then plus sine of t. Fantastic. So that's our solution, actually. That's our general solution, which is pretty crazy. So essentially what happens is that these two end up being part of our, let me see if it's these two or just this one. I'm trying to see how that works. I guess it's just this one ends up being a part of our, yeah, just this one I think ends up being a part of our particular solution, where these two end up being part of YC. And yeah, that's applying these initial conditions. So it's a little interesting if you want to compare the two methods. Now, obviously, the method we just used is a little lengthy. What makes it lengthy, though, is the process of partial fraction decomposition. But yeah, we didn't take any derivatives at all. With undetermined coefficients, you take derivatives, which isn't even bad because there's no actual integrals involved, but it just shows the usefulness of the machinery that Laplace implies. Great. So now I'm going to erase this, and we're going to do one more example. I think 2 is enough for this video, or else it'll be way, way, way too long. And we'll see what that entails. So let's take a look at that one next example right now. All right, so here we have this next and last example for this video. And it is a second order non-homogeneous differential equation. Very similar to the previous one we saw, but it's a little crazier. There's more terms here. This non-zero side is kind of crazier a little bit. We have a polynomial plus an exponential, so that's going to be interesting. And then notice here we have x instead of y as a function of t, but that's okay. So now let's see if we can solve using Laplace. So if you take Laplace of each side, let me get started here. So if you take Laplace of x double prime, again, we're going to call Laplace of x capital Y, just for simplicity. Now Laplace of x double prime, much like Laplace of y double prime, is what? It was s squared y, and then I guess it was minus s times y of 0, but here it's x of 0, which is 3, so it's going to be actually 3s now, minus y prime of 0, so again x prime of 0, which is negative 2, so minus negative 2 is actually plus 2, and then minus 4 times Laplace of x prime, which is s times y minus x of 0, which again is adding 2. I'm sorry, x of 0 is 3, so it's minus 3, my mistake. And then plus 3 times Laplace of x, which is capital Y. Here, if you don't mind, I'm going to distribute this negative 4 just to kind of make things go by a little faster. So it's going to be negative 4sy, and then negative 4 times negative 3 is actually going to be positive 12. These two will actually combine to 14 on the left. And if you look at the y's, what are the y's combined to? Well, we saw kind of an interesting fact last time. And let's see if we get a very similar thing here or not. Also notice we have a negative 3s before we consider those. So let's not forget that. So all terms are accounted for. Now the ones I underlined in red all have y in common. And if you pull the y out of those, what you get actually is s squared minus 4s plus 3. And you'll notice that s squared minus 4s plus 3 is indeed the characteristic equation of the left-hand side of the original differential equation. Notice the coefficients are 1, negative, or 3, matching those, and the amount of primes match the powers, which is nice. And we saw that in the previous example as well, so that'll actually be a common pattern throughout, as it turns out. Now when you take Laplace of this side, Laplace of t squared is 2 over s cubed, so it's going to be 6 over s cubed. And in fact, let me write that here, because we're going to, I don't think, no, actually, no, it's fine, it's fine. I was going to say it's going to be untouched, but I want to do something actually. Minus Laplace of t is going to be 1 over s squared, so it's going to be 8 over s squared. And then Laplace of 8 is going to be 8 over s. Okay, now Laplace of e to the negative 2t is 1 over s minus negative 2, which is 1 over s plus 2. But then times 15 is going to be 15 over s plus 2. And now what I actually want to do is combine these into one fraction. Now why I want to do that is because we're going to eventually divide by this. And as it turns out, if we divide by that and those gain those denominators, then we actually have to partial fraction decompose each 4 of these terms. I don't want to do that. I'd rather partial fraction decompose one fraction opposed to many. So let's do this. Let's multiply this top and bottom by s plus 2. This top and bottom by s and s plus 2. This top and bottom by s squared and s plus 2. And finally, this top and bottom by just s cubed to get a common denominator. Now let's see what we get. Now, of course, the common denominator is going to be s cubed times s plus 2. Good. But now what do we get in the numerator? Well, let's try to combine that off to the side here. So if you distribute 6 into that, you get 6s plus 12. That's fine. If you distribute negative 8s into that, you get negative 8s squared minus 16s. If you distribute positive 8s squared into that, you get positive 8s cubed plus 16s squared. And then finally, you get plus 15s cubed. Perfect. And now combining like terms, the s cubes combine to 23s cubed. The s squares combine to positive 8s squared. There we go. Squared. And then the s's combine to negative 10s. And then finally, we have this guy, which is just alone, so it's plus 12. Perfect. So now the next and kind of final step here is to solve for y. And to solve for y, we're going to add those to the other side. Well, I guess add and subtract that to the other side. So it's going to be y is equal to, so let's see. It's going to be this thing, so I'll kind of rewrite it actually. 23s cubed plus 8s squared minus 10s plus 12 all over s cubed times s plus 2. And you'll see why I'm offsetting this in a moment. Now I want to add this and subtract that to this side. So it's plus 3s minus 14. But we simultaneously, well not simultaneously, but after doing that, we want to divide by what's multiplied to y. So notice I'm not writing that here because we want to divide by it. Now, to save us a little bit of time, I'm going to actually factor this. Notice it actually indeed does factor, if you haven't noticed already. As s minus 1 times s minus 3. Of course, negative 1, negative 3 multiply to positive 3 and add to negative 4. So when you divide each of these by those two factors, they join the denominator here, s minus 1, s minus 3. And then here we just gain those in the denominator, s minus 1, s minus 3. And then if we want to combine this into one great fraction, which again is beneficial because otherwise we have to partial fraction decompose two things and not one, and I'd rather decompose one thing, not many. So we're going to multiply this whole thing, top and bottom, by s cubed, s plus 2. So it's going to look a little crazy, but I don't think the partial fraction decomposing part will be too bad. But let's see, if we FOIL 3s minus 14 and s plus 2 first, and then distribute s cubed after, well, let's distribute s into this first. We get 3s squared minus 14s. And then distributing the 2 into that, we get plus 6s minus 28. And then finally distributing s cubed into this just adds the power of 3 to each of these. So that becomes well actually these combine, don't, so let's do that first actually. So these combine to negative 8s minus 28. And remember, it was all multiplied by the s cubed, so that just adds 3 to every power, so that becomes 5, 4, and 3 to those powers of s's, good. And now adding those to this numerator, because I'll have the same common denominator now, finally leaves us with y is equal to all over s cubed times s plus 2 times s minus 1 times s minus 3. In the numerator we have, so notice there are no s to the 5th and s to the 4th, so let's write those. 3s to the 5th minus 8s to the 4th. The s cubes actually combine to negative 5s cubed. The s squared is the same, so it's plus 8s squared minus 10s plus 12 because everything else is the same, of course. Great. So now I'm going to erase all this, write this up on top, and now we're going to get into the partial fraction decomposing part of the problem. All right, here we go. So this is going to be a little crazy. In fact, I'm kind of questioning why I'm even doing this, but we deserve to see this. So let's take a look. So the partial fraction decomposition setup will be, we have a over s, I guess it's s cubed, so that's fine. A over s cubed, b over s squared, c over s, and that's because we have a repeated factor of s. And then there's no quadratic here, so it's just literally going to be d over s plus 2, e over s minus 1, and then f over s minus 3. That's not too bad. But now we want to combine this into one fraction, compare the numerator to that numerator. All right, well, that's going to be a little interesting. It's going to be kind of long, so we're going to probably have it staggered a little bit. So I'm not going to write what we need for a common denominator, but I'm just going to say it out loud. So this already has s cubed, but we need these other three. So a is going to be multiplied to s plus 2, s minus 1, and s minus 3. So is b, but b needs an s to get that s cubed. S plus 2, s minus 1, s minus 3. Already it's so much space. And then c needs an s squared to get that s cubed. And then it also needs, again, that s plus 2, s minus 1, and s minus 3. Okay, now finally for the last three here. D, what does D need? Let me actually move this over because I think we need even more space. But D needs s cubed. It already has s plus 2, but it needs the other two, s minus 1 and s minus 3. And very similarly, E also needs s cubed. And it needs the other two denominators that it doesn't have, which are s plus 2 and s minus 3, to get a common denominator. And then F needs s cubed, and it needs the other two, which are s plus 2 and s minus 1. And this will actually now make this whole expression all divided by this common denominator. So in fact, that whole fraction will be equal to this, in which case we don't care about the denominators, we only care about the numerators. So this crazy long expression being the numerator must be equal to the original numerator. So equal to 3s to the 5th minus 8s to the 4th minus 5s to the 3rd plus 8s squared minus 10s plus 12. Whew. So it seems crazy, but we have some implied values here to plug in for Heavysets method. And since we have 6 variables, these 4 values, when we plug them in, hopefully will give us 4 of those, because there's 4 values. So 4 of those 6 variables, so we'll only need to find 2 of those 6. So let's take a look. So when we plug in this, here we need s equals 0, s negative 2, and s equals 1, and s equals 3. And that's again by setting each of those factors equal to 0. So when we plug in 0, well, the only surviving one will be a actually, because anything multiplied by s or power of s will be 0. So that's going to be, let's see, when you plug in 0, that's 2 times negative 1 times negative 3, that's positive 6a. Equals over here, we end up just getting 12 on the right, because anything involving s is 0. So dividing by 6 gives us a is 2. Right. Let me just make sure on that. Yeah, so that wasn't so bad actually. Now what about when s is equal to negative 2? Let's actually try 1 first, because I feel negative 2 is going to be kind of crazy. It may not sound crazy, but we have powers, and I think it'll get kind of crazy. So let's see what happens when s is equal to 1. So when s is equal to 1, all of the s minus 1s become 1 minus 1, which is 0. So ignore any term involving s minus 1. That one's gone, that one's gone. So the first three are gone. This one's gone. That one's not gone, but the last one is. So when you plug in 1 here, you get 1 to the third, 1 plus 2, 1 minus 3. That's going to be 3 times negative 2, which is negative 6e. Equals, when you plug in 1 here, you just basically combine the coefficients. So notice that's going to be, the h's cancel, and then we get 3 minus 5 is negative 2, and negative 2 minus 10 is, that's interesting. So let me see this again. So these cancel out, 3 minus 5, again, all the s's are 1s, all powers of s are 1 when s is 1. So the h's cancel, 3 minus 5 is negative 2, negative 2 minus 10 is negative 12, negative 12 plus 12 cancels to be 0. So actually e is equal to 0. That's interesting. So now let's see what happens when s is equal to the rest. Negative 2, for instance, that one's going to be a little interesting to plug in. But anything involving an s plus 2 will be 0 in a very similar way for what happened for s minus 1 when s is equal to 1. And the only surviving term actually will be this one. Now when you plug in negative 2, you get negative 2 to the third, which is negative 8. That's going to be negative 3. Negative 2 minus 1 is negative 3. And that's negative 5. So let's see, what do we end up with? So it's 8 minus negative 8 times negative 3. So they're all negative, I guess. So it's going to be 8 times 3 times 5. Right, so 8 times 3, that's going to be 24, and 24 times 5 is 120. So it's going to be negative 120 actually. So you get negative 120d. Let me just make sure on that because it seems a little different than what I got before. Just trying to see here. I guess it's fine. Let's just go with it and see what happens. So now when you plug in negative 2 onto the right-hand side, what do we get? Well, we get... It's going to be a little long to do by hand, but that's fine. Negative 2 to the 5th is negative 32 times 3 is negative 96. Negative 2 to the 4th is positive 16. 16 times 8 is going to be 128. So that's going to be negative 128. Negative 2 to the 3 is negative 8. Negative 8 times negative 5 is positive 40. Negative 2 to the 2nd is positive 4. 4 times 8 is 32. Negative 2 times 2 times negative 2 is going to be positive 20. And then we have finally plus 12. Plus 12, good. So a lot of interesting things happen. So notice when you add the positives together, here we get, well, those actually combine to 44, or you can see like this. These combine to 32, 32 plus 32 is 64, 64 plus 40 is 104. So actually these just combine to 104. And these are both negative, but if you actually consider, I guess maybe these two better first. 104 minus 96. Well, 100 minus 96 is 4, so 104 minus 96 is 4 more than 4, which is 8. So really what we end up getting is negative 128 plus 8, which is negative 120. And look at that. So what was that word about? We end up getting d is equal to 1 when dividing. Nice. So it's not too bad. We get nice values so far. Kind of what I expected for us to get. Right, so now we need to plug in finally s equals positive 3. So let me erase this work here, and let's see what we get when we plug in s to be positive 3. Well, first we need to see what happens on the left. So on the left, we're going to get anything with an s minus 3 goes to 0, so that goes away. So the last surviving term is the one involving f. So when you plug in 3, 3 to the third is 27. And then 3 plus 2 is 5, and 3 minus 1 is 2. So it's 5 times 2 is 10. And then times 3 to the third again is 27. 27 times 10 is 270. So we get 270f actually on the left. On the right, what do you get when you plug in 3? Well, 3 to the 5th is 81. 81 times 3 is 243. Oh, I actually didn't do that right. I'm sorry. 3 to the 5th is 243, not 81. And then 3 times 243 is actually going to be 729, I suppose. Now 3 to the 4th is 81. 81 times 8 is 648. 3 to the 3rd is 27. 27 times 5 is 135. And 8 times 3 squared. 3 squared is 9. 9 times 8 is 72. 3 times 10 is 30. And then plus 12. Whew. So let's see. This is kind of close with the positives and negatives. That I think is the best way to figure these out, by the way. Just kind of compare positives to negatives. But actually, let's just subtract these first. So that's kind of interesting. Notice if we did 700 minus this, you get 52. But since we're doing 729 minus that, we get 29 plus 52. And 29 added to 52 is actually going to be 81. Right, because 50 plus 29 is 79 plus 2 is 81. Yeah, good. So it's going to be 81. And then minus 135. I'm trying to think if we can add maybe better. So let's do this. Let's combine the negatives here. We get negative 165. And then let's combine these two to get 84. And then 84 added to 81. I think I like that better. So that's not, oh, look at that. So this is nice. 80 plus 80 is 160. 1 plus 5 is 5. So these combine to 165. But 165 minus this 165 combines to 0. So that means our f is actually 0. So we got quite a few zeros here, which is nice. So good. So let me actually write that here on top before continuing. So we know a is equal to 2. We know d is equal to 1. We know e is equal to 0. And f is equal to 0 as well. And that's kind of nice because the zeros allow us to basically eliminate some of these in the equation. So when e is 0, that one's gone. When f is 0, this one's actually gone. And that's really it. If you want to replace d with 1, we can do that in our equation. And a with 2, we can do that as well. And was that it? I think that's it, because now we only need b and c now. Wow, great. So now I'm going to erase this below, and we're going to plug in nice values in for s to find b and c. And I'm assuming we're going to get a system of equations. And let's take a look. All right, so the values we plugged in were 0, negative 2, positive 1, and negative 3, or positive 3 actually. And the next nice value to plug in would be negative 1, and then positive 2 actually. But I'll say positive 2 because I think this may take a little bit of time. Now notice when you plugged in those nice values, a lot of these factors on the left went to 0. That won't happen here. So it's of particular interest to see what happens to s plus 2, s minus 1, and s minus 3, because those are pretty common factors here in this equation. So I'm going to just arrow over to what we get when you plug in negative 1 into these. And you get positive 1, negative 2, and negative 4. So namely, the product will be positive 8. So jumping into this, that product is 8 times 2 is going to be 16. That's going to be negative 1 times 8, so it's negative 8b. That's going to be negative 1 squared is positive 1, so it's c times 8, so 8c. And here that's only s minus 1 and s minus 3, which is still positive 8 actually. And negative 1 to the 3rd is negative, so it's going to be negative 8 altogether. And now when you plug in negative 1 into this, all odd powers will be negative 1, so we change the signs of the ones with odd powers of s. Even powers of negative 1 will be positive 1, so we'll leave those even powers of s to the same sign. And what we end up getting here is actually going to be negative 3 plus 8 plus 5 plus 8 plus 10 plus 12. So again, I only changed the signs of the ones involving odd powers, which were really these three here. So notice they changed signs. Everything else remained the same. In fact, this should have remained negative 8, so my mistake on that one. And that's good now because notice those 8's cancel. And actually, if you add these, you get, let's see, that's what's that? It's 27, right? It's 22 and 5 is 27, minus 3 is 24. So we get 24 there. But if you subtract 16, 24 minus 16 is actually going to be, well, actually, no, these combine to 8, actually. So it's going to be 8 minus 8b plus 8c. So I'm getting a little ahead of myself, I guess. But that's equal to 24. If you subtract 8 there, then you get negative 8b plus 8c is equal to 24 minus 8, which is 16. But then, of course, dividing through by 8 gives us negative b plus c is equal to 2. Awesome. So now I'm going to erase all of this here, lift this up there, and now we'll start plugging in s equals 2. and see if we get something nice. All right, here we go. So now again, we want to plug in s equals positive 2. We already plugged in s equals negative 2 for that factor, but not positive 2. So now when you plug in s equals positive 2, well, s plus 2 will be 4, 2 minus 1 is 1, and 2 minus 3 is negative 1. So the product will be negative 4. So we're going to have negative 4 times 2, that's going to be negative 8. This will be b times 2, so it's 2b times the product is negative 4, so that's going to be negative 8b. Here there's going to be 2 squared is 4. 4 times negative 4, because the product again is negative 4, is negative 16. So it's negative 16c. Good. 2 to the third is 8. These two multiply to negative 1. So negative 1 times 8 is actually negative 8. Good. And now what do we get on the right? Geez. Well, we saw something, we actually plugged something similar. We plugged in negative 2 and got something. So it wasn't too bad, I don't think. Let's see what happens. So 2 to the 5th is 32 times 3 is 96. 2 to the 4th is 16. 16 times 8 is 128. I remember that. 2 to the 3rd was 8. 8 times 5 is 40, so it's negative 40. 2 squared is 4. 4 times 8 is 32. 2 times 10 is 20. And then plus 12. So let's see what this combines to. Right, let's just, again, group up the positives and negatives. So if you look at the positives, only those three. This is nice. Those combine to 44. And 4 plus 96 is 100, so it's going to be 140, actually. That's good. And then the negatives, which are these three, actually, what do those combine to? Well, 40 and 20 is 60, and 60 and 28 is 88, so that's minus 188, which is actually negative 48. Okay. So, all right, so this whole thing is just negative 48. Now, these combine to negative 16. So if you add 16 to this side, what's the difference between 48 and 16? I guess it's 32. So it's going to be negative 32. So we have negative 8b minus 16c is equal to negative 32. Again, just like we saw with s equals negative 1, we can divide by 8. Well, let's actually divide by negative 8. So if you divide by negative 8, you get b plus 2c is equal to 4. So it's not too bad looking of an equation. And in fact, combined with this is super simple to solve for, actually. I see right away, if you add them, the b's cancel, you get 3c equals 6. So divide by 3c is 2. But I want to show you that. So I'm going to erase this, lift this up, and we'll solve that system. All right, fantastic. So we have this system, and it's a pretty nice one, because when you add straight down, like I said earlier, the b's cancel. C plus 2c is 3c. 2 plus 4 is 6. Divide by 3, you get c is equal to 2 right away. Plugging that into this one, well, that becomes 0, doesn't it? Because negative b, so we plug that into the top equation, we get negative b plus 2 is equal to 2. So if you subtract 2, you get negative b is 0, which in fact just means b is 0. So, right, so let's include that now here. So now we know b is 0 and c is equal to 2. So we only have 3 surviving things of the 6. So the partial fractions was a little crazy, as I said it would be. And in fact, in any differential equation you want to solve for by using the Laplace transform, yeah, that will be the hardest part of the problem, is finding the partial fraction decomposition of things. And of course, combining fractions is a little complicated too, but it's not too bad, it's just tedious really. So I'm going to erase this now, and we're going to take Laplace inverse of each side, because remember, this whole thing is equal to y, but if you don't recall, y is Laplace of x. So to take Laplace inverse of each side just gives us x by itself, so let's do that right now. All right, here we go. So I've cleared some things up. So these are the 3 surviving terms of our partial fraction decomposition, and I just replaced y with Laplace of x, might as well. So that means x is going to be what? It's going to be Laplace inverse of each of these. Now, Laplace inverse of 2 over s cubed, that's actually known as is, and that's just going to be, well, t squared. Laplace inverse of 2 over s, I guess you can pull out the 2 if you want, but Laplace inverse of 1 over s is just 1 actually. So this is plus 2. And then finally Laplace inverse of, it would probably be helpful to write this as 1 over s minus negative 2. But yeah, we know that is, in fact, that's kind of what we did here to get 1 over s plus 2. when we took Laplace of this at the very beginning of things, if you remember that. And we get plus e to the negative 2. Fantastic. So this is x as a function of t. That is our general solution to this initial value problem. So it was quite lengthy, but remember, the longest part here was the partial fraction decomposition. So the better we get a handle on that, then the easier this process becomes. But you can kind of see, really, this is it. So if you take Laplace on both sides and solve for y, if y is Laplace of x using some properties and so on, combine things into one fraction, you get this. Then, if you partial fraction decompose that, you get this. Y is equal to Laplace of x, and then applying the Laplace inverse, you get this right away. So really, it's like a few lines if you take away all of the complicated parts of combining fractions into one and decomposing a fraction. Great. So I hope you enjoyed this video. We only did 2 examples. They were long, but at least they showed the properties in a nice way. And right, that's all I wanted to say as far as this goes. And yeah, if you want to watch my other videos, I have plenty of other videos. And like always, thanks for watching, and I'll see you then.